what happens in ADMM is that, so in ADMM, if you remember, we have a problem of minimizing some dual function, which is a function of lambda w and some z, for example. And the thing is that we want to minimize over everything, but then it's not separable here. So what the ADMM is doing is actually trying to use coordinate descent kind of approach. So using dual decomposition to somehow separate, to remove this lambda from here actually. And then trying to use this distributed kind of, let's say dual decomposition and these dual functions, okay? But then the thing is the problem is not decomposable, so then what it does, ADMM is just using coordinate descent kind of approach to alternately optimize over W and Z, okay? But then you have seen in non-convex optimization that there are two different approaches or class of approaches. The first one is using this alternating minimization of coordinate descent there, where you minimize over one coordinate, then over the other coordinate. So this is actually ADMM, dual decomposition plus coordinate descent. Here, this approach is taking another class of approaches, which is successive approximation. So just imagine that this is the shape of the function. In in ADMM, what it does is that it says that this function here is not separable, meaning that we cannot separate that over different workers. Then let's go with one coordinate on one worker, another coordinate, another worker. Here, they say that, okay, let's approximate this function with another nicely behaving function, which is now separable. So this is the whole idea again. Again, dual decomposition usually plus making it separable instead of using coordinate descent, using this successive kind of approximation. And then you can imagine that since we are using this successive approximation, at every iteration, we will find this solution, but then this is not the optimal solution anyway. And you can have this approximation, somebody else can say that, okay, instead of this approximation, I'm giving this approximation. Then the solution is different, right? So that's why that depending on your approximation, even if you find the exact solution here, it's just one approximation. Somebody else can give another approximation and the exact solution is different, right? And then, so the thing is that if this sequence of these solutions can converge, and this sequence of solutions can converge, it means that essentially you could start from this sequence of solutions and then assume that there were some kind of error over that. So instead of finding the solution, any solution here within this range should be fine with you, because starting from this point, you can use another approximation and then go closer and closer to the optimal solution. So this is the whole idea here. Due to some approximation, it means that you can, of course, find the exact solution here, but it just doesn't matter because at the end of the day, this is one approximation function. You could use another approximation function ending up to another solution, right? So essentially, it says that a sequence of those approximate solutions should be found and then approximate with some theta. So this is my understanding from that.
Yeah.
Okay.
Perfect. Excellent. And I also soon we will resume more formally this a bit more formally this kind of comparison with ADMM. Let's go on. And I left a little bit of suspense because I have given now this approximation that it's a way to again to approximate this function capital OA of alpha. And now I'm giving the algorithm. And the algorithm is that generalized called the primal-dual algorithm. Let's say I have this matrix capital A distributed according to the columns to the various nodes or processors according to this partition. Then we initialize the alphas and the V in this manner. Remember, V, if I go a couple of slides back, is defined in this manner, and is the coupling variable now after doing the approximation. Then if we initialize V in this manner, we can run the iteration in this way. For every k, every node here does this minimization, having as input V and alpha at the time t, bt and alpha t, and then does the minimization and finds the delta alpha k, which is then used here. This is there is a little typo again. Should be with a parenthesis. This delta alpha goes here and is to define the next updating of the variable alpha k at t plus 1. And we define then delta vk in this manner as the product of the result of this minimization for the matrix A that belong to the party k, to the node k, to the processor k, and then is this delta vk that is actually communicated to everybody. So, here the communication scheme is that this node has to send the delta vk to everybody, and everybody has to do the same. So it's a broadcasting to everybody. And so then every party or node can locally compute this updating of the variable v as the previous v plus the sum of the delta vk. And this either is done centrally at a third party, or if every node gets and then the third party sends it to the various nodes, or simply all the nodes they have a replica, an identical replica of this updating. So again, what is the only thing that is exchanged here is now the delta vk. That is communicated, and the communication is a broadcast, so everybody has to communicate with everybody else. The delta vk. Fantastic. Now the question is that is natural and obvious here is how if this algorithm converges. And by the way, this algorithm we can apply it directly as it is to the problem here, the one with the big O of A, or to the problem here. It's just a matter of changing the notation. The difference is that the application of algorithm 1, the previous algorithm, to this case here, which is called algorithm 2, and to this case here, which is called algorithm 3, the difference is that here we have a matrix A, and here we would have A transpose. So we would have a different way of partitioning. It will not be a partitioning of the columns as before, but is of the rows, because we are using A transpose. And therefore, if you look now at the machine learning problems that I've given in the table, that would typically correspond to here doing some training, and here because the rows would be used for training, and here the columns it's more features. Okay, algorithm 2 and 3, they are therefore basically the application of algorithm 1 to the two instances of the same problem. And then the final here natural question is, these updatings, do they converge of this algorithm? Yes, the answer is not always, of course, but the answer is yes, under certain circumstances that are here clarified by this theorem. And in this theorem says that we choose this specific gamma, and let be theta the quality of the local solver that gives the solution. Then after a certain time t that depends on this expression, and this expression depends on this expression, and finally on this expression here depends on this. After this sequence of inequality, we know fine there is a capital T, after which the optimal we compute the optimal solution with a desired accuracy that we call epsilon g. And here this is expectation of the function that we wish to minimize, computed in alpha bar, where alpha bar is the average of the alphas that have been computed from capital T0 to some capital T. It's a metric to measure convergence. Okay, there is no better metric than this, because if you develop the proof here, you arrive at this kind of metric, which is also a good metric to ensure convergence to the optimal solution within some epsilon g. And we take an expectation in general. We have an expectation because the assumption is that the local solvers, they might be even randomized solvers, so they would give the solution in a random sense, and that's why we have the expectation here. If the local solvers are precise, and for example we are locally solving a convex optimization problem, we wouldn't have any expectation here, and everything would follow in the same manner. And this result is derived for the case of convex GI and L-Lipschitz GI star. Under other, if I go forward here, I have there is other results for strongly convex GI and smooth GI star, and we would have another set of results. Now I don't have the time to comment on this, but it's along the similar lines. Then therefore, based on the properties of the function, the regularizer, and the lossy here, that could be smooth, no smooth and separable, or convex, or no strongly convex and separable R, we can apply algorithm 2 or algorithm 3, and the convergence of those algorithms is ensured by theorem 2 or 3 that I very quickly mentioned before. And again, in the proof of this algorithms, on these convergent properties, there is no major mathematical miracle. You have just to apply the properties given in assumption 1, 2, 3, and 4 as a set of inequality. The proof of these results, they just start to pose this inequality, this argument, and then you exploit the inequalities, left here, right, another inequalities, and another inequalities, and then you impose that everything is less than some epsilon g, and poof, the proof is done. So just a long algebraic exercise. Okay, and now finally, before going to next, let's have a little bit more formal comparison with the ADMM that we have mentioned, that as mentioned. If we take, we could apply the ADMM to now this problem here or to this problem here. And why we are doing this? Because ADMM also solves, can solve the machine learning problem with distributed computation. And we are interested, since we have studied it in the previous lecture with the Yuan, we are our natural question is why now this general framework that we are studying today works better than ADMM. To answer this natural question, we apply ADMM could be to this formulation or this formulation. I have chosen, I follow the paper, and I've applied the ADMM to the formulation B, the one with the convex conjugate. Would be identical if I would apply to the case a capital A, which is actually you can find in the appendix of the paper. And okay, then I apply the ADMM method, and I introduce the usual consensus constraint, because I wish to distribute the computation among the various processors here or nodes. We apply the usual machinery of ADMM, and we would arrive at these 3 iterations. Each, this is local, because it's a processor K. This is local, this is processor K. And again, all this is a trivial exercise now out of the previous lecture. And you will find the detail in the appendix of the paper that is in the background of these slides. Now the major difference compared to algorithm 1 of a few slides ago is that we have this step here. We have also we have still in ADMM a global variable that has to be updated, similar to the general method of 2 slides ago. But in ADMM we have this additional term that is the proximal updating. And in general, this might be not easy to. It's an additional computation that has to be done, and in general might not be easy to distribute it. So we will need a third party that does this, or we have to come up with some ingenious way to distribute the computation of this term here. So with further communication, with further computations. So it's the general method that I've just introduced before doesn't have this in a sense it doesn't have this term. So it's less computation, less communication. And what is remarkable is that now in the paper that you will see listed at the end of the lecture, there is now a thorough numerical comparison of this framework here with the ADMM. And today there is no analytical comparison. So yet another research here activity that would lead to a strong publication would be to make an analytical comparison between the ADM method of last lecture and the method that I've introduced so far, to really show analytically if it's possible, what would be working better, or what is precisely the trade-off communication computation. And on the paper here that I'm using for this lecture, they have a thorough numerical comparison, and it's amazing how faster and more efficient is this general method compared to ADMM for many machine learning problems, the one that were listed in the table before. Do you have questions, curiosities that you wish to discuss? Objections? Yes.
I didn't get that the reason that we find the expectation of difference between OA and OB, because these two functions are some equivalent functions to our original problem.
Where there is the expectation.
Yeah.
So the question is why we have the expectation here in this convergence results. We have these expectations, and before we were not really speaking much about randomness. The expectation comes from the fact that the local solvers here, they will give, in general, for the sake of generality, these solvers can be also randomized solvers. So they can give, and as such, we can have the local solutions as random variables. That's the intuition behind this expectation.
Yeah, I think the question was what is the difference between A and B, because both of them are
Aha.
equivalent.
The difference here in the argument between this, good, because very good question. This is exactly the duality gap. So that will tell us is a quality of the optimal solution. If you go back in the beginning of the slides, I have spent some little time to highlight that if you get a solution of this and we have a solution of this, they give us, since this is the dual, B is the dual of A, we can get the duality gap that is a measure of how good or bad is the solution. And now this is used here in the machinery of the proof. In the reality, we would run rather the optimization using this or this. We don't use both. But in the machinery of the proof, we can arrive at these convergence results, which ultimately tell us that the method converge, and which is a practical insight. Although it wouldn't be practical to run simultaneously the primal and the dual. Excellent, very good. Other questions? Fantastic. If not, now we jump to the next part here of today's lecture. So let's go to the quantized distributed gradient descent, and now we introduce a further concept here that is typical in communication network, which is that when we exchange information, not only we might have limited channels in terms of availabilities, and so in the method that I have just summarized here, we were only exchanging the delta B. Instead, in ADMM, we were exchanging another variable, and we have the proximal update. Here, in this part 2, we are introducing another problem typical of communication, if you like, and is a quantization of the information exchange. Instead of sending the perfect variable here, we are doing sometimes even heavy quantization. And sometimes these quantizations can be so hard up to just 1 bit. So instead of sending this analog value here, we can have just a +1 or -1, and in certain cases we still have convergence of these distributed machine learning tasks. Okay, so that's what now this is what our art would like to hear a beautiful theory on distributed solution method for machine learning problems with quantized information exchange. That's what we have been always dreaming to, but unfortunately today I will only give a very small but still meaningful result in this line of research that still has much to be written, has very, very much to be written. And I will only focus on a very special case, on special machine learning problem with a special structure and in deterministic setup. Now I am introducing the quantization, and I am also a general network setup. So let's forget a little. Let's forget about this. It's another setup in the sense that we can have whatever here network, and I'm assuming that the function of our machine learning problem is separable and is only written in this term. So we don't have, this doesn't capture all the many machine learning problems that we were looking at before. It's a more specific formulation. And we assume that there are some nodes, a number of nodes in the network, and every node I has also a number of neighbors, and the number of neighbors of node I is denoted with matcal of an I. So here also this function fi is owned directly already at the node I. Okay, it's already divided, and there is already an owner. Then, good, what we wish to do is to, as usual, we would like to compute the optimal solution of the machine learning problem with distributed computation, and we can, given the formulation of the problem here, we can directly apply the methods of a couple of lectures ago. Okay, we just minimize the function here, our function, and we introduce again the consensus constraint, so that the local omega, the local wi is equal to the w's of the neighbors. Just go back to a couple of lectures ago, I'm doing that. The great novelty of this part here, compared to what we have done before, is that in the consensus updating and iterations, we are not sending the precise variable, but we are sending a quantization of the variable. And instead of exchanging the wi at iterate t, w is owned and node I at time t, as in the previous lecture, I am sending a quantization zit, where this d is the result of some quantizer function. It would be whatever quantizer you like. So the question is, with such a quantization, do we have convergence here? Does it work always? The answer is that no, it's in certain cases we have convergence, not always. And let's formalize therefore the algorithm. We have already seen the distributed gradient descent, GD, in the previous lecture. Now I will introduce the quantized gradient descent that is identical, except that instead of exchanging the WIT, I will exchange the quantization. And the algorithm works like in this manner. Every node, I, or processor, has weights, and these weights are the Aij, from j from 1 to n. And these are the typical Aij. If I go, I forgot to mention, I believe, somewhere before. No, I didn't say clearly that, it's next slide. Yeah, well, these Aij are the ones, are the classic weights in the consensus that are used, and then we will see later they well to satisfy double stochastic matrix, and so that we have very beautiful properties on the spectral radius and so on. And these are owned at the various nodes. Then for every iteration, the node updates the local decision variable at node I at time t plus 1 with this equation. This equation is almost identical to the distributed gradient descent that we have already seen, except that I'm using ZJT, that is the communicated variables from my neighboring nodes and these variables are quantized. Okay, just to keep our attention focused somehow, here we have some network of nodes. The nodes could have neighbors like this, and this network wants to solve this machine learning minimization problem, f of w, which is the sum over the nodes of fi of w. To arrive at this common global w, to arrive at the distributed solution of this problem, we apply the distributed gradient descent of the previous lecture, and in other words, to do this, the node I does an update of the variable wi, t plus 1, which is given by that equation. Okay, every node keeps doing this, and hopefully they will achieve the result of minimizing this function. With the difference now here that we are sending the information of the communication link here is quantized. It's not the W that is transmitted, but it's the ZI that is transmitted, which is a quantization of WI. And again, we have seen the details of this in the previous lecture, and maybe with a slightly different notation. And here the novelty is that in this updating equation, we have an alpha and an epsilon that is somewhat new compared to, they are arranged in a different way compared to a couple of lectures ago. The quantization here in general is an operation that can be seen as a random procedure, because we could have, if this is a set of values, and these are all this is a continuous values, okay, this is a continuous axis, and we have certain points that are our quantized value. So we say that if say wi is this value, if this is the wi, for example, then we could take the closest point, and this will be zi. This is zi, and this is wi. Sometimes the point is closer to here, sometimes the point is closer to here. So we have a quantization error that can be modeled statistically. Actually, the quantization itself is can be done in a probabilistic term, which is what people have done in this study. And I will soon speak about that. So with this setup, let's consider our usual assumption that we are the only ones that are needed in the machinery proof to arrive at convergence results. We have this set of assumptions. The function is differentiable and smooth with parameter L. The function fi are strongly convex with parameter mu. And we have then the quantizer. This quantizer here, it's has to have two important properties that are very natural. The first one says that if I take the expectation, when I do the quantization and I get the z, after the quantization error, if I take the expectation, I must have exactly the variable that I wanted to quantize. So this is an unbiased quantizer. Okay, that's the meaning. And then the variance here of the quantizer is bounded with some sigma square, which is also natural. Okay, so again, I have some analog value, I quantize it to some point, and I commit an error, I do an error. This error is random, and what I wish that is that over many errors that they do, on average, the quantization, the quantizer gives the right value, the initial value. And also the error in this quantization that I do is bounded. It's not I don't do an infinitely big error. Natural assumption. And then the other assumption is that the matrix A for the consensus is usually the symmetric and doubly stochastic matrix that people have been researching in the last 20 years. So it's A equal A transpose, A1 is equal to the vector 1, A transpose 1 is equal to the vector 1. Okay, with this simple, just with this assumption, despite the fact that we have a quantization, we can have still convergence of this quantized distributed gradient method. And the result is this, that suppose that the assumptions of the previous slide hold, and let be delta a scalar between 0 and 1 divided by 2. Let's have two arbitrary constants, C1 and C2, and let be epsilon be like this, and alpha like that. So it's a bit involved with definitions. Well, but then under this assumption, we have that iterating in this manner the computation of the optimal solution, we have that there exists a capital T, so that we, after that time of iteration T, 1, 2, capital T, we will be as close to the optimal solution as this O of this term. Okay, and this is the usual order notation here that you could have seen in the previous lectures. This convergence results depends on many things, such as this function, this L about the function, the mu of the function, the number of variables, these arbitrary constants C1 and C2, the matrix A, the diagonal version of the matrix A, and beta, which is the difference between the largest and second largest, between the second largest and the third largest eigenvalue of the matrix A, and that's the beta. And this is an interesting result, which is, it looks a bit, it's kind of a crocodile expression, but it's practical, can be practical, because it tells us that it's a sort of bound on the optimality, and so we can tune the parameters so that we, after a number of iterations, we achieve such an optimal solution. And what is interesting and remarkable, if I go a couple of slides back, that this result is not obvious because of the way this equation here is written, with the 1 minus epsilon here, and this epsilon here, and alpha epsilon, is such that if I take the expectation of this, it's not a biased, it's not an unbiased expectation. We have the term Z here, the quantization, that carries a quantization noise. And this quantization noise, in these equations, iteratively keeps accumulating. But despite this fact, we can have that this accumulation of quantization error will not diverge. Something that is not obvious. And that's the beauty, in my opinion, of that result that we have just seen. What else I should mention here? Yeah, this is that's it. So it's a well-contained now result for a specific problem formulation, and but still it's meaningful. One here could argue, but can we apply the same reasoning of this case to here, to our previous problem? Of course, yeah, we can. Nobody has done it before, and we don't know if we would achieve convergence, and if, despite of quantization, we could have a machine learning task that is accomplished, among others. And we could add many other things here on the formulation of the objective functions and so on and so forth. Okay, I realize that I've been very quick here. I apologize. I had only 24 minutes. If you don't have questions, you are justified. But do you have questions? Do you have questions?
When we take the distributed gradient descent, there we have a parameter gamma that is actually updating based on the delta that we get here from. So essentially that does some kind of a quantization by itself.
Yeah.
Because you're not taking the actual value and updating. So if you actually move the, let's say, the quantization error that you get over here, I mean, it's going to be uniform. So if you model that gamma as some kind of a quantization in the form of a uniformly distributed variable,
Yeah.
can you not somehow achieve
Yeah.
similar convergence?
So that, yes, is an excellent question. The distributed gradient descent that we have seen in the previous lecture, that's also a modification, we can say, of the transmitted variables, and then this could be seen as a form of quantization. And the answer is yes, but will be a very particular quantization, and might not be the one that you decide on the IoT network, when instead you would like to transmit just 3 bits, say. So I'm not sure how easy it would be to map that on a quantization. But it's a very good, it's an excellent observation, which also allows me here to clarify that in these iterations of the quantized gradient, we would achieve convergence also in a sort of would be obviously this could be somehow an obvious result if this z would give some stochastic subgradient, okay, which is not always the case. So that's why there is a more particular result given by the paper that is behind this section here. Excellent. Other questions? Okay, no questions. At this time you are justified. Next part, it's impossible to hear. We have only 3 minutes, so I will just relax. Since we are finishing the lecture, so you don't go out and you are dizzy. Let's go slow. This we went now in a sequence of results that have a degree of generality smaller and smaller. We started with this big approach. This we were fought here. It's a number of years of research, and then we went to this result. This very interesting conference paper. And as you have seen, it's not that general. And then we go to this result here. It is even less general and even more particular. And the difference is that here is the stochastic gradient descent that now we are quantizing. The difference also, compared to what I've told you before, is that is even a third scenario, is a third setup, because in this in the previous case, in this quantized distributed gradient descent, we had that the nodes, they owned a function fi, and they were doing local iterations to arrive at the global solution. In this third case that I'm introducing now, and I will write here, that is the parallel quantized stochastic gradient descent. It's even a simpler case. I have a function f of w that has to be minimized and is associated to some machine learning problem. We have also a network of nodes But these nodes, they all are measuring a stochastic gradient of this common global function. Okay, so it's even it's a more ancient case compared here, because here there is already something that is distributed, that we can do distributed computation. In this line of research is still so fresh, it seems to be at least so fresh, that we have only the case, still the case, where everybody here is doing some measurement that it's called as Gi tilde of W, is a measurement M of the stochastic, of the gradient, actually of the stochastic gradient of this function that I'm calling M of F. Okay, so every node does a stochastic measurement of the stochastic gradient, and it will exchange a quantized such measurement. So all the nodes are observing the same thing, and all the nodes, they know the same, actually they have access to some stochastic measurement about this common function. And this is the setup that this third paper is exploring. And since I am running out of time, and have actually no more time, and the only thing that I can tell you is that we arrive at similar convergence results with somehow similar flavor as before, but again in that even more particular and ancient setup. Yes, that's it for today.